Hello, hello. This is Daniel. I am starting up a new series that I am aptly naming PEP Talks, which stand for Post Employment Podcasts. I will be recording audio while I'm driving home from work every day, hopefully. That's the goal. And I will be talking and discussing topics that are interesting. Topics that I know a thing or two about due to my education and upbringing that most people probably don't. And I will dive into that in the first one, explaining that. But I wanted to preface it here and say that while I'm doing the series, I will be driving home from work for the most part. And I also, for YouTube's sake, I wanted to not just have audio, so I'm recording video game content for the most part and putting that as the background. And I'll be playing different games and doing different things throughout this series. So, without further ado, let's get into the first pep talk.
Hello, I am driving home from work. Anyway, I am realizing that I know a bit of information that most people in the planet do not know, and that most Americans do not know. So I graduated with a degree in aerospace engineering and a minor in project management, and some of the stuff that I talk about and deal with every day is just stuff that people don't know. So I want to talk about it. Mainly, I started blowing the minds of my coworkers with some of this stuff. Like, second day on the job, we started talking about particle physics because one of my coworkers, who he does project engineering, was just super interested in it. And so I want to, just share the knowledge I got because it's interesting. I'm also, like I said, driving while doing this, and I'll probably put a fill underneath it. But yeah, so let's get started, I suppose. So light. Do you know how light works? I didn't figure out. It took me so long to figure out how light works, because no one ever teaches it. No one teaches you something as simple as light until you get to high-level college courses. So, in middle school, you're learning about atoms and you're learning about, stuff, the Niels Bohr's model, and plum pudding models, and all sorts of things about subatomic particles, but you don't learn what light is. So then you get to high school and you're in a high school physics class, and they talk about, forces and vectors and energy and stuff, but you don't learn what light is. So then, if you're in a STEM major like I was, you get to Physics 1, and you're studying, again, forces. You're studying masses on springs. You're studying things that have harmonic motion, that oscillate, that typically have frequencies. And you still don't learn what light is. Then you get to Physics 2. And when you get to Physics 2, what ends up happening is you take the concepts from Physics 1 and you start applying them to things like energy and things in the world beyond springs, that you can see and not see in some cases because they're too small or too esoteric or just not visible phenomena. But you don't quite learn what light is. You're pretty close, though. You are pretty close. They hint on it at the end of Physics 2 in college, and they're like, wait till you get to Physics 3. Then you will learn what light is. And I'm like, okay, cool. So at this point, I'm, in my second or third year of college. I think it's my third year. And I'm taking Physics 3, Physics 270, with Physics 271 as a lab. And they taught me what light is. And let me tell you, being in college nowadays, most of the time you don't need a textbook. And if you do need a textbook, you really don't read it. But in that class, I kid you not, I have never read through an entire textbook for any class before. And I barely reference them. But for that class, I had to read the entire textbook because light is awesome and complicated and amazing. And it's super non-intuitive how it works. So that was probably one of the hardest classes I had in undergrad was what is electromagnetic radiation. but what is light? And for aerospace engineering, it's kind of, we don't focus on it too heavily, even though radiation is the number one thing that kills you in the space. You know, like, you'll die of lack of oxygen in a couple minutes, but you also die of radiation poisoning in a couple minutes if you're unprotected in a vacuum. But yeah, so regardless, got to learn what light was. Now, you may have heard wave-particle duality. You may have heard the fact that light is weird. It behaves sometimes like it has mass, and it behaves sometimes like it's a particle, but it also behaves like it's a wave. But it also, as far as we can tell, it doesn't have mass, from what we can observe. So, I'm entering a traffic circle right now, and traffic's picking up. But yeah, anyway, so light, it's a wave and it's a particle, which is cool, but it's complicated. So when you think of particles, you think like, you know, a baseball is a particle compared to the field that it's on when you're playing it, or like, again, traffic circle drama. You know, electron, neutrons, and protons are particles that make up an atom. Like, that is pretty standard stuff. So photons, which is the more scientific-y name for light, photons, or electromagnetic waves. Both are referring to light, by the way. Just one describes the wave side, the other describes the particle side. Behave strangely. So you probably have heard the speed of light, and you've probably seen Einstein's E equals mc squared there. Well, E is energy, m is mass, and c is the speed of light squared. And the speed of light is 3 times 10 to the 8th meters per second, which, well, it's close to 3 times 10 to the 8th. It's an approximation. It's like 2.998 or something. 2.98, but don't fact check me on that one. It's close to 3 times 10 to the 8th. Anyway, so speed of light, stupid fast. It's faster than anything else that we can imagine, observe, or even record, because we operate in systems that require light. Your eyes, you can't see anything faster than the speed of light, because light needs to happen for our eyes to work. What else? Like, you don't have anything that has mass. Well, assuming light doesn't have mass, you don't have anything that has mass traveling at the speed of light either. It's actually like an exponential energy function of how much energy you need to get to the speed of light. Although it's doable, because E equals mc squared, there's an equal sign there. So if you take energy and you take mass and you want to get it to the speed of light, well, I mean, it's a lot of energy to accelerate mass. But the point is, and I don't think you can use the equation that way. You're not balancing velocities. But the point is, you can't accelerate things to the speed of light, because it takes a near infinite amount of energy, if not an infinite amount of energy, if they have mass. Yet, light, which is literally everywhere, it's more common than, well, I can't confidently say there's more photons than there are atoms in the universe, but I wouldn't be surprised. Like, light is absolutely everywhere. And yet, all of it's traveling at the speed of light. Well, in a vacuum, per se. You can have light that travels less than the speed of light, ironically, even though it's called the speed of light, if it travels through something. And I'll get to that in a bit. But yeah, so I'm starting to learn what light is. So, light's a wave and a particle. Big whoop. I heard that all my life. Well, what does that mean? It means that light can interact with other things like it's a wave or a particle. And you're like, okay. So, when particles collide, what happens? Well, a neutron is a particle that has no charge. If it collides, there's subatomic particles, there's a whole bunch of weirdness that goes on. But sometimes it will attach itself to some protons, and then you get some electrons orbiting, and you get matter. So particles touch each other. Like, that's a natural thing. when light, so this is interesting. This is actually how mirrors work. When light touches matter, specifically electrons, it is absorbed by those electrons. It rams into it, and because light is energy, the electron, we'll go with electrons, absorbs energy. Now, when this happens, electrons, you can measure their energy based on where they're located in the orbitals of the atom. And if you don't know what an orbital is, I can explain it, but that's something I actually learned in middle school and high school. It just basically electrons orbit atoms and rings, and they orbit. The lower and closer they are to the nucleus of the atom, the less energy they have. They're more stable. And it's a measure of like potential energy and actual kinetic energy. There's a cool pairing, and it's a bit chaotic. And this is also assuming classical Newtonian physics, but it's cool. Anyway, so electrons will absorb photons. They'll absorb energy, and when that happens, they jump up to a higher orbital. Now, what happens is they want to be stable. They want to reduce their energy. So, they reduce their energy by emitting photons, which is crazy. So, that's how mirrors work. If you have a mirror, and you're looking in a mirror, or if you shine a flashlight at a mirror, you think, oh, I'm shining light at this. And guess what's happening? The light's hitting the mirror and it's bouncing off. Wrong! The light is not bouncing off. The light is getting absorbed by the mirror, and then the mirror is emitting new light. It is emitting new photons that are completely different than the photons that hit the mirror. But they happen at an incident angle that is equal to the angle of incoming light, because of geometry and weirdness and magic space voodoo. But anyway, I digress on the magic space voodoo. The light that hits a mirror, or hits any object from that matter, reflects off, not as that light that hit it, because it's traveling at ludicrous speeds. It's traveling at light speed. Like, you can't just hit something that's traveling at light speed and change its direction all of a sudden. I mean, you get stars and stuff and supermassive gravity wells that can bend light, but they're not making it do a 180. So what actually happens is, the light is absorbed by matter, and the matter then emits new light, which is pretty darn cool. Now, mind blown, right? That's just step one. That's just, like, practical. Like, when you're looking in a mirror, you're seeing light that your face is emitting that is most likely has hit your face from an outside source, like there's lights in the room. Your face is absorbing it. Your face is then emitting that light back out, and then that light's going to the mirror. The mirror is absorbing it. It's emitting it back out. It's going to your eyeballs. Your eyeballs are absorbing it, and our eyes are so cool. They turn that into electrical signals and through rods and cones and a bunch of more biological nonsense, and are able to make that something we can see and comprehend. Like, we can understand and comprehend light in the visible spectrum. Which, I guess I should hit on that for a second. Spectrum. So photons are like a singular thing, right? And photons have a fixed energy, but light is also a wave. It comes in a spectrum, which means it has different frequencies. Now, what a frequency is just how many cycles per second something happens. So the unit is a hertz for the base unit. It's like if I slap my brother 30 times in a minute across the face, my hertz, my frequency is 0.5. Because I've done it, I do it once every 2 seconds. Or if I slap him 120 times in a minute, my frequency is 2 hertz. Don't try this at home, but if you want to, ask permission first. Anyway, so that's frequency. So light has properties of frequency too. What it means is it oscillates in its path. So remember when I said that like light's traveling at the speed of light? You can't really change its path easily. Well, ironically, the path it's taking is a curved one. It travels straight, but it's oscillating along its path. Think of it, it's like vibrating. It's vibrating along its path, although vibrations can take different forms of oscillations. And like sound waves, for example, are vibrating, but those are compression waves, which are a different kind of wave than light travels in. Light travels in a sinusoidal type waveform, generally speaking. And you can mess with the amplitude, and you can mess with the frequency, and you can change the characteristic of the light by doing that. Light has a spectrum, and we only see part of it. If I'm in my car, so I can't look it up exactly off the top of my head, but I believe it's between 300 and 700 nanometers is the visible frequency of light. But you might be thinking, what the heck? Or, sorry, that's the visible wavelength of light, because I don't think I've explained wavelength yet. Frequency, you have a hertz, right? The physical measurable distance, like, inches, meters, miles, that kind of stuff. Measurable distance. The measurable distance between the peaks of something that's vibrating, that has a frequency, is called its wavelength. It's how far in space, or in reality, has this thing traveled for one cycle. That's its wavelength. So, light that oscillates, which is all light, I don't know of any. You can get radio waves which have really low oscillations, but they're still oscillating. Has a wavelength associated with it. So, wavelengths and frequencies are tied to each other. They go hand in hand. I think one's actually the inverse of the other, if I remember correctly, with some more magic voodoo thrown in, and you throw in some amplitude stuff. But again, I'm in my car. I don't have that equation memorized like I should. I really should, though, but I can picture it. Anyway, so light has a wavelength, and we only see a small section of the possible wavelengths of light out there. Pretty cool. At least I think so. Anyway, moving on. And that's, again, I'm not trying to go down a rabbit hole, but I bring that up for the next point because I wanted to talk about, I talked about this with my coworker today to blow his mind in the morning. Gamma wave spectroscopy. You may, if you're nerdy, have heard that term before, but you might not know what it refers to. Gamma wave spectroscopy is a really cool thing that us humans have figured out how to do by using the effects of light, both as a wave and as a particle, to measure stuff. So, imagine you're in space and you're looking at Pluto, which I remember back when Pluto was a planet. I grew up with Pluto being a planet, but sadly, Pluto is not considered a planet by the general public, but the general public is wrong. Pluto is a planet. But anyway, you're looking at Pluto, and maybe it's moon Charon, which is huge. It's like 50% the mass of Pluto or something. And you want to know what Pluto's made of, right? But you don't want to land on Pluto, because Pluto's a pain to land on. It's all dusty, and it's not really that solid, supposedly. But you want to figure out what Pluto's made of. So what do? You shoot a frickin' laser at it, and that tells you what it's made of. Now you might be asking yourself, how does shooting a frickin' laser at Pluto tell you what it's made of? Well, gamma ray spectroscopy kicks in. What gamma ray spectroscopy is a combination of the wave-particle duality of light, used in a practical sense. So, remember when I said that when electrons in particular absorb photons, they jump up to energy levels? So, photons carry with them a certain amount of energy, right? And if you look at the full spectrum of light, which is infinite, by the way, because you can have infinite subdivisions of wavelengths, gamma rays, gamma waves, gamma light is on the side of the spectrum that has super high energy, and super high frequencies and super tiny wavelengths. You gotta pack it all in, pack that energy in. It oscillates really quickly. So what you do is you shoot a laser at something, typically gamma waves. And making a gamma laser, by the way, is like, that's already big, scary. No, don't do that. You're shooting radiation. Well, there's radiation all around you right now, but you're shooting like the deadly kind of radiation out of a laser. Be warned. Don't make gamma wave lasers. But in case you do, you can shoot it at stuff, and that stuff will absorb the gamma waves in its electrons. Now, it absorbs so much energy per photon that the electron doesn't just jump one orbital. It's absorbed more energy than an orbital typically can contain. So it might have to jump up 2 orbitals, or 3 orbitals, or 4 orbitals, or even 5 orbitals, or more, or less. Might be 1, but it has to jump up a ton of orbitals to absorb a gamma photon, right? And again, it's an infinite spectrum. I'm just making a generalization. Now that electron still wants to be in its base state. So to get to its base state, it still needs to bleed off energy, and it still needs to emit photons and jump down orbitals. The thing is, though, it does that in discrete steps. Like an orbital for an electron orbiting has a fixed amount of energy in it that it needs to maintain that orbital. So when it jumps from an orbital to another orbital, it emits a photon of a very specific energy level. And we can measure that by the photon's wavelength, which is also related to its frequency. And we can measure that. Now, for sake of argument, let's say it jumped up 4 orbitals, and now it needs to jump back down 4 orbitals, just from the one photon hitting. It's going to emit 4 photons to jump back down, and each of those photons are going to be of a specific energy level, specific wavelength, and a specific frequency. And they're going to emit back out, kind of like a mirror does, at an angle that we can predict and expect. So, what that means is that for the price of 1 photon at high energy, you now got 4 photons of lower energy coming back at you. And we have special devices that can measure that energy. Spectroscopy devices. Spectrum measurement devices. That's spectroscopy. So anyway, that light comes back at you, it's measured, and you can tell exactly what kind of matter you hit with a photon because we have lab tests that we can reference. Like, if you have a piece of aluminum in a lab and you shoot it with a gamma wave and it bounces back 4 photons, well, we measure that. And we have that on the record and we write it down. So then if I shoot Pluto and Pluto emits the same 4 photons in the same frequency band that the aluminum in the lab did, then Pluto is made of aluminum when you have it. That's cool. And if you want to look it up, there's like frequency bands of different elements you can look up. It's pretty cool. They give off different, light. Not all of it's in the visible spectrum, so usually it's colorized to match it to the visible spectrum, but it's not all in that frequency range. Anyway, so when atoms give off this stuff, we measure them. And it gets complicated because not everything in the world you're measuring is one thing. Like, the surface of Pluto might be a mix of silicon and aluminum and carbon and some sort of nitrogenous compound. And, well, if that's the case, we might have plant life on Pluto, but I doubt that. Maybe it's like boron. And it's a mix of all these things. Now, if you have that happening, all those things are going to absorb that light, and all those things are going to emit light, and you're going to get a mess of light back. But luckily, we have developed enough instruments and sensitive enough measurement tools that we can actually differentiate that. Because what you do is, if you get a bunch back, you kind of like overlay them over each other, and you take all the elements we have and we do know, and there's wave spectrums, and you pull them out. So you pull out the one for aluminum. If all 3 or 4, let's say 4, I don't know if it is 4, but if all 4 bands match up on that thing for aluminum, and they're in the right spots, but there's also other bands, well, aluminum's there. So you pull out aluminum from the measurement, you subtract it. So then that leaves a few less bands, and you keep doing that until you figure out exactly what's in there. And it's a process of elimination. So through the duality of light, being a wave and a particle, we can measure matter. Like, thousands and millions of miles away. It's pretty cool. Although, well, we do it for some things too. I don't know if we've done it for exoplanets yet, but I'm pretty sure you could. Although, because of how light scattering works, which I did promise I would get the light scattering when I talked about mirrors. Because of how light scattering works, I don't know how accurate spectroscopy is at long distances. I know there's the inverse square law of light, meaning that light scatters at a rate that is inversely proportional to the distance traveled. Meaning that, like, if you travel a meter, well, light will scatter a certain amount. But if you travel 2 meters, light will scatter 4 times that amount. It's inversely proportional. And you can literally look all this stuff up on Wikipedia. I'm just trying to be interesting while driving home from work. Anyway, so light scattering, yay! Let's talk about that. And also light absorption. I do want to do this and talk about emissivity. So, not everything in this world is a perfect mirror, and no mirrors are perfect mirrors either, as far as I'm aware. Nothing has 100% emissivity. Now, emissivity is the property of matter that determines how much light it reflects back. So, something with a low emissivity doesn't give you as many photons back as you put in. So let's say, let's say I got a McDonald's Happy Meal box and it's red and yellow and it's made of cardboard. And let's say the emissivity of that cardboard box is like 6.6. Now let's say I shoot 100 photons at it. If I shoot 100 photons at it, about 60 are going to come back at me. That's an way oversimplification of emissivity, but that's the general gist. And you get light diffusion and light scattering because of that, as well as just light absorption. So things that don't reflect light well, like if you have a black t-shirt on, like you're not as bright as if you had a bright white t-shirt on. Or similarly, like reflectors on your car or on your bike have high emissivity values. They take light in and they send it right back so that people can see you. They don't absorb it. Now, for the last 5 years, I've been biking on my campus, or the past 5 years, I should say. And my bike is all black. I got black tires, I got silver rims, but I got a black seat. I wear a black leather jacket when I'm biking in the cold and it's not raining. My bike is blacked out. It's really hard to see at night. So I got reflectors on there to help it be seen. Because otherwise, the emissivity value is so high or low in this case. Emissivity value is so low that you couldn't see my bike because light isn't reflecting off my bike. And at night, there's only so much light that can go around. It's not like the daytime where the sun is literally bathing us in stupid amounts of radiation and everything is lit up and everything's bouncing the light around. Like, that's why we see during the day, because there's just so much light. There's so many photons. The waves are filling up everything. But at night, we don't really get that. The moon, though, gives us some, but the moon has its own emissivity value. The moon's just a giant mirror in space for the sun. Sunlight hits the moon, moonlight hits us. Well, sunlight hits the moon absorbs that light, and then emits its new light back at us. Anyway, so you get That's light absorption and emissivity. Light scattering and diffusion and that kind of stuff happens when you have light traveling at different speeds. Now you might be wondering, how can light travel at different speeds? I thought the speed of light is how it travels. And you're right. The speed of light is what it travels in a vacuum, which means there's no matter for it to travel to. But we live in a planet, on a planet that has matter, just in the air we breathe. So when light is traveling from the car in front of you, its headlights, to you, well, it's taillights, because if it's in front of you and its headlights are coming at you, you have bigger problems than worrying about light scattering. You need to pull over or dodge that car. But if its taillights are hitting you, then those taillights, the light traveled through matter. It traveled through the air. And some of it was absorbed by the air and reflected back out, probably. But because of the lack of density of the air compared to solid matter, there's not as much stuff in it, as thick as it is, you get light hitting you for the most part. A little bit less. That's why, like, cars in the distance don't have as bright of lights as cars close to you, because some of it's absorbed by the air. But for the most part, you can see the stuff in front of you. So, light is being absorbed partly by the air, but it's also being diffused and diffracted because it is traveling through a medium. Now, because air, like I said, air's not that dense, so it's not diffused and diffracted that much. You wouldn't notice it as much. But there's a fun little experiment you can do. Is take a glass of water, or take a glass, fill it with water, and put a pencil inside it. And then look at the pencil from outside. Now, when you do that, the pencil will appear like it goes in one spot, and then it'll have like a sharp, it will move over, and then the pencil will continue in the water. That's because the light is affected by the water. It's traveling at a different speed, even though the water is translucent, hopefully. Hopefully the water you drink is clear. Anyway. And if it's not, then you probably put some, like, sugar in it. And a flavor packet, but I digress. Anyway, so speed of light's affected when it travels through certain mediums, and that causes the light to hit you at different points. So the light will enter the glass from outside the glass, go through the glass, hit the water, diffract and travel slowly, go through the water, also go hit the pencil and bounce around so you can actually see the pencil. And then it will leave the water, go through the glass again, and come back to you in the air. And there's a speed discontinuity when it does that. So the light that's coming at you, both from the outside of the glass and the inside of the glass, are hitting your eyeballs in a weird way, where it is diffused, and the image itself, because remember, we see things as they appear, we don't see things as they are. The appearance is the pencil has shifted over considerably, but we know that the pencil has not moved. The pencil is continuous. Yet we see it the other way. It's an optical illusion. Same thing like on a hot day in the summertime, it looks like there's pools of water on the road, but there's not. That's an optical illusion of the heat displacing and diffracting the light in an interesting way, because hot air has different properties than cold air. And there's a lot of nuance to this, and I'm not getting into the numbers as much, but that's a general, like, how light works for your daily life. And it took me reading an entire textbook and half a year with a lab class attached to it of trying to figure this stuff out, to just understand that much about light. Now, that same class talked about electromagnetic flux and waves, and other sorts of, aspects of light, but electromagnetic flux is, I only bring that up because that's a mix of electro, which is, light, electromagnetic flux is a mix of electricity and magnetism, That's what I want to talk about next time, I think. And if not that, I'll talk about something else that's cool. But the mixture of energy in form of electricity and the mixture of magnetism is where we get a bunch of other cool properties in physics that, again, you don't learn that in middle school or high school, like how magnets work, or like how does literally anything that runs electricity for work. You don't learn that stuff. But I did, and it took Physics 3 to get to it. So the average person, like college students, are the 1% of the world, and then on top of that, most college students don't take high-level physics classes. And that's kind of where I'm at with that little bit of knowledge. Now, I know a bunch of stuff about a bunch of stuff, but I also know that I don't know a ton of stuff about many things. The more educated you are, the more you realize how little you know. And so I say all this humbly this is just a practical way of understanding something that's ubiquitous, something that's common to your daily life. And I hope you enjoyed it, as I am now pulling into my driveway, which is cool that this took exactly as long as I needed it to. Yeah, so if you like this, just send me some feedback. I'll probably still make them, regardless if you don't like it, because I am not so swayed by your opinion of me. But regardless, I hope you had fun. I hope you learned something. And I hope you'll join in next time. See ya.